Why does a $40 spool of premium fluorocarbon snap against a dock piling on the very first strike, while a $7 spool of basic monofilament dragged across the exact same barnacles survives to land the fish? That is the exact question independent materials testing laboratories have finally answered, and the data they have uncovered completely shatters the marketing narrative you have been fed for decades. We are looking at a global fishing tackle market worth billions of dollars annually, built almost entirely on arbitrary pound test ratings and packaging claims that have absolutely zero legal requirement to match reality. The major manufacturing holding companies, the heavily sponsored tournament professionals, and the massive retail chains know exactly what happens when you put these highly marketed lines on an Instron 5543 tensile testing machine or a transverse abrasion rig. They know that what they print on the cardboard box is often a complete mathematical fabrication designed to control your purchasing habits and keep you replacing your gear on their schedule. Today we are tearing down that wall of misinformation. We are going to count down the top 10 fishing lines based entirely on actual, verifiable scientific laboratory tests, measuring precise cross-sectional diameter against true linear break strength and cyclic abrasion resistance. By the time we hit the #1 spot on this list, you will know exactly what your money is actually buying down to the molecular level. So hit that subscribe button right now, because the rigid science of polymer extrusion is about to expose every single lie hiding inside your tackle box. Starting off our countdown at number 10 is a staple of the industry that perfectly illustrates the chemical limitations of standard nylon monofilament, and that is Berkeley Trilene XL. To understand why this line performs the way it does in independent laboratory testing, you have to look at the exact molecular chain of standard nylon polymers. Nylon is formulated with amide groups, which inherently absorb water at a microscopic level. When independent polymer laboratories, like the testing facilities at the University of Akron, put these standard monofilaments through rigorous testing protocols, the results are shocking. The water molecules actively disrupt the hydrogen bonds within the polyamide chains, acting as a chemical plasticizer. This means the material becomes softer and stretches more when it gets wet. While the marketing department spin this chemical flaw as being extra limp for better casting, the laboratory reality is brutal. Independent tests running 12-pound Trilene XL on an Instron machine show that while the dry line might test at an acceptable breaking strain, its transverse abrasion resistance drops by a staggering 50% after just a 10-minute soak in water. The industry completely hides this catastrophic loss of structural integrity behind slick branding, selling you a product that fundamentally degrades the moment it touches the water. Coming in at number 9 is the baseline standard for braided line, the basic 4-carrier gel-spun polyethylene, most commonly recognized in products like the original PowerPro. The engineering behind ultra-high molecular weight polyethylene, or UHMWPE, completely changed the fishing industry, but the geometry of how it is braided is where the market manipulation happens. A 4-carrier braid means the line is constructed by weaving together 4 individual bundles of microscopic fibers. When tackle testing laboratories put this line through a 3,000-cycle unilateral abrasion test, dragging it repeatedly across a rough ceramic guide under heavy tension, a fascinating physical phenomenon occurs. Because there are only 4 carriers making up the total diameter of the line, each individual bundle is relatively thick and possesses a significant amount of physical mass. This raw mass provides a sacrificial layer of material that takes a substantial amount of time to sever completely. The industry pushes anglers toward much more expensive 8-carrier braids, claiming they are universally superior, but the lab data proves that when subjected to brutal perpendicular friction against structure, the crude, thick strands of a basic 4-carrier PE braid actually resist catastrophic failure longer than the ultra-thin strands of premium weaves. Sitting at number 8 is the highly engineered realm of dual extrusion copolymers, specifically exemplified by Trickfish X-rated copolymer. This is where chemical engineering attempts to solve the inherent weaknesses of standard nylon. Instead of forcing a single melted plastic through a die, copolymer manufacturing utilizes an advanced co-extrusion process with 2 concentric annular openings. The machines extrude a highly crystalline polymer blend in the center to serve as a high-density, load-bearing core designed strictly for linear tensile strength and minimal creep under sustained pressure. Simultaneously, an amorphous, much softer polymer blend is extruded around that core to form an outer jacket. This softer jacket provides high impact resistance and allows complex knots to seat perfectly without generating the friction heat that burns and weakens the main line. Laboratory testing proves that this dual-layer construction significantly reduces knot slippage and increases shock absorption without sacrificing the tensile baseline of the core. Before we continue down this rabbit hole of polymer science, drop a comment below and tell me exactly what chemical polymer is spooled on your primary setup right now, whether it is standard nylon, PVDF, or PE fiber, so we can clearly see exactly who the major marketing departments are successfully targeting in their ad campaigns. Moving to number 7, we enter the world of basic fluorocarbon with Seaguar Invis X. The active chemical compound here is polyvinylidene fluoride, or PVDF, an unreactive thermoplastic fluoropolymer originally developed for industrial applications. The entire marketing campaign for fluorocarbon rests on its refractive index. Water has a refractive index of approximately 1.33, standard nylon sits around 1.53, and PVDF is roughly 1.42, making it much closer to water and therefore less visible to fish. Furthermore, PVDF is roughly 1.85 times denser than nylon, meaning it physically sinks faster. However, the engineering trade-off that the industry refuses to put on the box is the mechanical stiffness of the crystal structure. When independent testing facilities put basic fluorocarbons into an Instron machine utilizing air-gripping clamps to simulate knot tension, the data is highly uncomfortable. Because the PVDF material is so dense and rigid, tying a standard knot causes the line to physically crush under its own radius. The independent tests consistently show that standard fluorocarbon has a significantly lower knot strength percentage compared to standard copolymer of the exact same diameter. The tackle industry relentlessly pushes the invisible angle specifically to distract you from the fact that you are losing up to 20% of your breaking strain the exact second you tie your lure to the line. At number 6, we have Sufix 832, a product that exposes the intense thermal dynamics of braided line manufacturing. The fundamental problem with ultra-high molecular weight polyethylene fibers is that they have incredibly low melting points. When a massive fish pulls drag, the PE line running through your rod guides generates localized thermal events, creating micro-friction heat that actively melts and compromises the gel-spun fibers. The engineering solution implemented in Sufix 832 is the insertion of polytetrafluoroethylene, completely known to the public as Gore Performance Fiber, or PTFE. By weaving one single strand of PTFE alongside 7 strands of standard Dyneema PE, the line utilizes the lowest coefficient of friction of any known solid material. When subjected to independent cyclic bend over sheave testing, where the line is run back and forth over a pulley thousands of times under extreme tension, the PTFE strand acts as both a permanent, solid-state lubricant and a thermal heat sink. The laboratory results prove that this composite weave handles exponentially more cycles before thermal degradation occurs compared to pure PE braids. The major tackle companies do not want to talk about thermal degradation because explaining the thermodynamics of line failure under load immediately exposes the glaring chemical weaknesses of their most profitable standard braided products. Breaking into the top 5, we look at Berkeley Trilene XT, a line that highlights the massive chemical differences hidden behind simple marketing words. While standard nylons are made of nylon 6, high abrasion monofilaments like XT are synthesized using nylon 6,6, which is created from hexamethylene-diamine and adipic acid. Those extra carbon atoms in the polymer chain completely change the mechanical properties of the extruded line. The chemical cross-linking drastically increases the yield strength and the overall stiffness of the material. When tackle testing engineers place this specific molecular structure on a specialized abrasion rig, running the line back and forth across a rough nail head or 800 grit sandpaper while completely submerged underwater, the results are undeniable. The nylon 6,6 formulation of the XT takes nearly twice as many friction cycles to sever completely compared to the standard nylon 6 formulation of the XL version. The industry purposefully markets these two completely different chemical structures side by side as simply being limp or tough, actively hiding the advanced chemical engineering profiles behind generic labels so that consumers never learn how to actually read a material specification sheet. Taking the number 4 spot is Tasline PE Braid, which completely exposes the severe lack of quality control and manufacturing tolerances in the mass-market fishing line industry. The dark secret of the tackle world is that most companies only batch test their lines once a month, allowing massive diameter variances and microscopic flaws to slip into the retail supply chain. Tasline operates under a strict microbatch testing protocol, utilizing an advanced Mark 10 air clamping tensile testing machine certified and calibrated by IDM Instruments. At their facility, every single 5,000-meter cone of raw fiber is subjected to destructive stress testing before it ever touches a retail spool. Furthermore, they record the data based on clamping friction rather than perfect hollow splicing. Splicing a line for a lab test spreads the tension load perfectly, giving a falsely high breaking strain that you will never achieve on the water. Testing the line with air clamps replicates the harsh shear stress and friction point of an actual fishing knot. The engineering data recorded from these machines proves that the advertised tensile strength of a line is absolutely meaningless if the manufacturing tolerances allow for even a 5% diameter variance along the length of the spool, because the line will instantly fail at the thinnest microscopic point, long before it ever reaches its theoretical breaking strain. Landing at number 3 is the ultimate paradigm shift in our countdown, representing the highest tier of PVDF engineering. Toray Superhard, Japanese domestic market fluorocarbon. The global tackle market will confidently tell you that all 100% fluorocarbon is exactly the same raw material, melted down into different spools. That is a blatant, highly profitable industrial lie. The comprehensive independent laboratory data, specifically the massive Tackle Tour Fluorocarbon Showdown, put these premium resins through rigorous dry and wet abrasion testing, strictly controlling for line diameter down to a 0.02 mm delta to ensure an absolutely fair scientific fight. The engineering reality is that premium JDM lines do not use standard extrusion. They utilize a proprietary multi-stage thermal tempering process. They bake the PVDF resin in specialized heating chambers to align the polymer crystals perfectly parallel to the longitudinal axis of the line. This molecular alignment creates a surface hardness that physically deflects microscopic serrations on rocks, dock pilings, and fish teeth. The independent lab results conclusively proved that Toray Superhard tested 47% more abrasion resistant than the baseline standard monofilament. And critically, it maintained that exact structural integrity even after being fully saturated in water. The advanced chemical cross-linking in the outer layer of this specific resin completely prevents the microscopic water intrusion that degrades cheap fluorocarbons. This is the mathematical, verifiable proof that you are not just paying for a fancy imported brand name. You are paying for an advanced thermodynamic extrusion process that the budget brands physically cannot replicate in their outdated factories. We have looked deeply at the chemical variances between standard water-absorbing nylons, dual-layer modified copolymers, baseline PE fibers, and highly tempered PVDF resins. But the mathematical reality of polymer science is about to get significantly more uncomfortable. The final 2 fishing lines on this laboratory test list do not just improve upon existing materials. They fundamentally rewrite the laws of linear tensile strength and physical knot mechanics. Before we continue into the complex realm of hollow core geometries and ultra-high molecular weight polyethylene braided under extreme industrial tension, you need to understand that the highly technical data we are breaking down here is exactly what the major tackle conglomerates actively try to bury beneath flashy packaging and paid professional tournament endorsements. If you want to keep arming yourself with the actual metallurgical and chemical data that dictates whether you land the fish of a lifetime or reel an afraid broken tag end, hit that subscribe button right now. The next 2 items are going to make you question every single dollar you have ever spent on bulk spools of conventional fishing line, because the engineering data we are about to expose completely dismantles the standard industry narrative and proves that almost everything you thought you knew about line strength is a mechanical illusion. At number 2, we completely abandon traditional knot physics and enter the structural engineering of Jerry Brown Line 1 hollow core braid. The fundamental mechanical problem with every single fishing line on Earth is the knot. Tying any knot creates a microscopic friction point and induces massive transverse shear stress across the polymer fibers, effectively reducing the overall breaking strain of the line by up to 40% the second you pull it tight, according to independent laboratory tests. The engineering solution to this catastrophic mechanical failure point is hollow core splicing. By utilizing highly specialized 16-carrier braiding machines, manufacturers create a continuous tubular structure out of raw spectra fibers. Instead of tying a knot that weakens the line, a monofilament or fluorocarbon leader is threaded directly inside the hollow tubular structure of the braid using a specialized needle. Under heavy tension from a fish, the woven spectra fibers naturally constrict around the inserted leader, operating on the exact same physical and geometric principle as a Chinese finger trap. The harder the fish pulls, the tighter the radial pressure becomes. When placed on an Instron 5543 testing machine, a properly spliced hollow core connection retains a staggering 100% of the line's original linear tensile strength. There is no knot, there is no transverse shear stress, there is no thermal friction burn, and there is absolutely no weakened failure point. The industry knows that massive offshore game fish are constantly lost because anglers rely on primitive friction knots instead of structural mechanical splices, but they continue to sell solid core braids because they are significantly cheaper and faster.